Picture the universe not as a crowded sea of stars, but as an endless, interconnected web, a delicate lacework of galaxies stretching across the darkness. Now imagine the gaps in that web, vast pockets of nothingness so enormous they could swallow entire galaxies without a trace. These are the cosmic voids, the ghost towns of the cosmos, where the usual rules of space seem to break down. They're not just empty, they're eerily, inexplicably barren, as if something has swept them clean of matter, light, and even the faintest whispers of cosmic radiation. And what's lurking in these voids? That's where the mystery deepens. Scientists have stumbled upon phenomena within these voids that defy every expectation, strange signals with no clear source, distortions in space-time that shouldn't exist, even hints of structures so massive they challenge our understanding of gravity itself. It's as if the universe is hiding its strangest secrets in plain sight, tucked away in these cosmic deserts where no one thought to look. Some of these anomalies are so bizarre they've been dubbed impossible by the very researchers who discovered them. And today, we're diving into 25 of the most perplexing, awe-inspiring mysteries hidden within these voids, phenomena that could rewrite the textbooks on everything we know about space, time, and the fabric of reality. This isn't just a tour of the universe's empty corners, it's a journey into the unknown, where every discovery raises more questions than answers. What if these voids aren't just accidents of cosmic evolution, but clues to something far bigger? What if the gaps in the cosmic web are hiding forces or dimensions we've yet to imagine? From unexplained radio bursts to shadows of ancient galaxies that shouldn't exist, the stories locked inside these voids are waiting to shake our understanding of the cosmos to its core. So buckle up, we're about to venture into the great nothing, and what we find there might just change how you see the universe forever. The Boötes Void isn't just empty, it's a cosmic enigma on a scale that defies logic. Picture a region of space so vast it could fit thousands of Milky Ways side by side, yet it's almost entirely devoid of galaxies. At 330 million light-years across, this monstrous void, nicknamed the Great Nothing, is one of the largest structures ever discovered and one of the most baffling. According to our current understanding of the universe, voids should still contain a scattering of galaxies, remnants of the cosmic web's delicate structure. But the Boötes Void throws that idea out the window. Instead of dozens or even hundreds of galaxies expected in a space this size, astronomers have found fewer than 60. It's like walking into a stadium built for thousands and finding only a handful of people scattered in the seats. So what could have caused such a staggering absence? One theory points to dark energy, that mysterious force accelerating the universe's expansion. Could it have stretched this region so thin that galaxies were ripped apart or pushed beyond detection? Others wonder if the void is evidence of something even stranger, an ancient collision with another universe, leaving behind a scar of nothingness. Then there's the more speculative idea. What if an advanced civilization, far older than ours, once occupied this space and somehow erased it? While that might sound like science fiction, the sheer scale of the void forces scientists to reconsider every assumption. Even the galaxies that do linger here behave oddly. Some appear stretched or distorted, as if the void itself is warping space-time in ways we don't fully understand. And then there's the eerie silence, radio telescopes picking up almost no background noise, as if the void is actively swallowing signals. It's a place where the rules of cosmology seem to unravel, leaving us with more questions than answers. The Boötes Void isn't just a hole in space, it's a challenge to everything we think we know about how the universe works. If the Boötes Void feels like a gaping hole in space, then the Eridanus Supervoid is more like a cosmic bruise, a strange, faintly glowing cold spot in the cosmic microwave background radiation, the afterglow of the Big Bang itself. Stretching an astonishing 1,800,000,000 light-years across, this colossal void isn't just empty, It's colder than it should be, as if the universe's memory of its own birth has been subtly altered here. When scientists first spotted this anomaly, they assumed it was a glitch, a statistical quirk in the data. But the colder they looked, the more unsettling it became. At the heart of the mystery is a question that rattles the foundations of cosmology. How could a void this size leave such a stark imprint on the oldest light in the universe? One explanation suggests that the supervoid's immense emptiness acts like a gravitational hill. Photons traveling through it lose energy, stretching their wavelengths and cooling the light we observe, a phenomenon called the integrated Sachs-Wolf effect. But here's the catch: the temperature drop is twice as large as our models predict. It's like stepping into a shadow and realizing it's far darker than the absence of light alone could explain. Then there's the eerie coincidence no one can ignore. The Eridanus Supervoid lines up almost perfectly with the so-called axis of evil, a controversial alignment of anomalies in the cosmic microwave background that seems to defy the cosmological principle, the idea that the universe should look the same in all directions. If this axis is real, it implies a preferred direction to the cosmos, a cosmic fingerprint that shouldn't exist. Some theorists whisper about even wilder possibilities. Could this void be the remnant of a collision with a parallel universe? Or is it evidence of exotic physics, like a phantom energy field stretching spacetime itself? The debate is far from settled. Skeptics argue that the supervoid might just be a chance underdensity, a rare but natural fluctuation in the cosmic web. Yet even they admit the numbers don't quite add up. Meanwhile, the cold spot stubbornly refuses to fade into statistical noise, haunting our maps of the early universe like a ghost in the machine. Whether it's a flaw in our understanding of gravity, a window into multiverse theory, or something entirely unforeseen, the Eridanus Supervoid forces us to confront an uncomfortable truth. The universe might be stranger and far less uniform than we ever imagined. We think of our Milky Way as just another galaxy in an endless sea of them, drifting through the cosmos like every other speck of light. But what if we're not just another face in the crowd? Studies reveal something startling. Our galactic neighborhood sits at the heart of a vast, diffuse void 7 times wider than average, stretching roughly 2 billion light-years across. Scientists call it the KBC Void, named after the researchers who discovered it, and its existence throws a wrench into one of astronomy's most cherished principles: the idea that there's nothing special about our place in the universe. This idea, known as the Copernican principle, has guided cosmology for centuries. From Galileo to Hubble, we've learned Earth isn't the center of the solar system, the Sun isn't the center of the galaxy, and our galaxy isn't the center of anything, or so we thought. The KBC Void suggests otherwise. If our local patch of space is unusually empty, it means we occupy a privileged position at the core of a cosmic anomaly. Imagine living in the only house for miles in every direction while assuming every other neighborhood is just as sparse. That's the paradox we're facing. What makes this void even weirder is how it could be tricking our measurements of the universe's expansion. Dark energy, that enigmatic force pushing galaxies apart, is calculated based on how fast objects are receding from us. But if we're sitting in a void, a region where gravity's pull is weaker because there's less matter around us nearby, galaxies might appear to be moving away faster than they truly are. It's like standing on a raft drifting out to sea and misjudging the tide's speed because you didn't realize your own platform was floating away. Some scientists argue this Hubble bubble effect could mean we've overestimated dark energy's strength, throwing decades of cosmological models into question. Not everyone's convinced, of course. Critics point out that voids this large should be incredibly rare. Statistically, they're almost impossible in our current simulations of cosmic structure. Yet here we are, right in the middle of one. Could it be a fluke, a 1 in a billion coincidence, or is it a clue that we're missing something fundamental about how the universe distributes matter? Then there's the eerie implication: if we really are in a void, it might not be the only one. What if the cosmos is peppered with similar bubbles, each distorting our view of the whole? It's a humbling thought that even our most precise measurements of the universe could be warped by the very emptiness around us. The KBC Void doesn't just challenge where we are in space. It forces us to ask whether we truly understand the rules of the game. The Lynx Supervoid is no ordinary emptiness. It's a cosmic puzzle buried deep in the fabric of space, so distant and strange that its discovery sent shockwaves through the world of cosmology. Located roughly 3 billion light-years away, this void spans an incomprehensible 900 million light-years, making it one of the largest and most isolated structures ever observed. But what truly sets it apart isn't just its size. It's the eerie way it aligns with other cosmic anomalies, forming a pattern that seems to defy the randomness we expect from the universe. When astronomers first mapped this void, they noticed something unsettling. It sits along a peculiar axis shared by the Eridanus Supervoid and other massive underdensities, as if the cosmos has a hidden skeleton of emptiness threading through it. This alignment isn't just coincidence, it challenges one of the core assumptions of modern cosmology, that matter should be distributed evenly on the largest scales. Instead, the Lynx Supervoid hints at a cosmic architecture we don't yet understand, a blueprint where voids and filaments might be arranged in ways our models never predicted. Then there's the mystery of the missing baryons, ordinary matter. The stuff that makes up stars, planets, and us should be scattered throughout the universe in predictable amounts. Yet when scientists tally up the baryons in regions like the Lynx Supervoid, the numbers don't add up. It's as if someone took a cosmic eraser and wiped away a staggering portion of the universe's building blocks. Some theories suggest these missing baryons might be hiding in diffuse, ultra-hot gas clouds too faint to detect, or perhaps they've been pushed out of the void by some unseen force. Others speculate more radical ideas. Could dark matter or even undiscovered physics be at play here? The Lynx Supervoid isn't just a curiosity, it's a laboratory for testing the limits of our knowledge. Simulations of cosmic structure formation struggle to reproduce voids this large and empty, leaving theorists scrambling to tweak their equations. Some propose that dark energy's repulsive force might be sculpting these voids more aggressively than we thought, while others wonder if our understanding of gravity itself needs revision. Every time we point our telescopes at this distant abyss, it throws back more questions than answers, reminding us that the universe's grand design is far from solved. What makes this void even more tantalizing is its silence. Unlike other cosmic structures that hum with the faint whispers of ancient light or the echoes of colliding galaxies, the Lynx Supervoid is a realm of near-perfect stillness. It's a place where the universe feels unfinished, as if something or someone left the job half done. Whether it's a key to unlocking the missing baryon problem, a clue to large-scale cosmic symmetries, or a signpost to physics beyond our current grasp, one thing is certain: the Lynx Supervoid isn't just empty space. It's a challenge written in the negative, daring us to read between the lines of nothingness. Deep within the cosmic microwave background, the faint echo of the Big Bang lies a chilling anomaly that has divided cosmologists for decades. Known as the cold spot, this mysterious patch of sky, detected first by the WMAP satellite and later confirmed by Planck, registers a temperature significantly colder than its surroundings. At first glance, it might seem like a minor statistical blip, but the numbers tell a different story. The cold spot's temperature dip is so extreme that the odds of it occurring randomly are roughly 1 in 50. That's like rolling a die and getting the same unlikely number 10 times in a row. So what could explain such a stark deviation? One leading hypothesis points to the Eridanus Supervoid, the colossal emptiness we explored earlier. If photons from the cosmic microwave background pass through a void, they lose energy climbing out of its gravitational well, resulting in a colder signal, a process called the integrated Sachs-Wolf effect. But here's the twist: the cold spot's temperature drop is about twice as large as even the supervoid can account for. It's as if we're seeing a shadow cast by something far stranger lurking in the void's depths. This mismatch has sparked wilder theories. Some researchers propose the cold spot could be evidence of a cosmic texture, a rare hypothetical defect in space-time left over from the universe's early moments, like a wrinkle frozen into the fabric of reality. Others go even further, suggesting it might be a bruise from a collision with another universe during the chaotic inflation period after the Big Bang. Imagine two soap bubbles brushing against each other in a froth of multiverses, leaving behind a faint, cooler imprint where they touched. It's a tantalizing idea, though skeptics argue it veers into speculative territory. Then there are the more mundane explanations. Could foreground dust or instrumental noise be distorting the data? Detailed studies have largely ruled out dust as the culprit, but the possibility of unseen systematic errors still lingers. The Planck team's own analysis concluded that while the cold spot is real, its origin remains ambiguous, neither fully explained by known physics nor definitively pointing to something exotic. What makes the cold spot so compelling is its refusal to fit neatly into any single narrative. It's a Rorschach test for cosmologists. Some see a cosmic defect, others evidence of parallel universes, and still others a statistical fluke magnified by our hunger for discovery. But if it is a window into something beyond our current understanding, a crack in the standard model of cosmology, it could reshape our entire picture of the universe's birth and structure. Until then, the cold spot remains one of the most tantalizing unsolved riddles written in the oldest light we can see. Threading through the darkness like cosmic highways, the Hercules Corona Borealis Great Wall and the Sloan Great Wall don't just defy expectations, they shatter them. These two titanic filaments, among the largest known structures in the universe, stretch across unimaginable distances, weaving around voids like borders around an empire. The Hercules Corona Borealis Great Wall alone spans an astonishing 10 billion light-years, a thread of galaxies so vast it challenges one of astronomy's bedrock ideas, the cosmological principle which states that the universe should look roughly the same no matter where you're observing it from. But when we peer into these structures, uniformity vanishes. Instead, we're met with a cosmic quilt stitched together in patches of staggering density and yawning emptiness, as if the universe played favorites when arranging its matter. What makes these walls so perplexing isn't just their size, it's their age. They formed when the universe was still in its adolescence, a mere few billion years old. Conventional models suggest such colossal structures shouldn't have had enough time to assemble. Imagine a skyscraper built overnight, its steel and glass snapping into place faster than physics should allow. That's the scale of the mystery here. Some theorists propose that dark matter's gravitational scaffolding might have accelerated their growth, creating dense highways of galaxies amid the void. Others wonder if our understanding of cosmic inflation, the universe's explosive early expansion, needs a rewrite. Could cracks in space-time have seeded these structures like frost spreading across a window? Then there's the Sloan Great Wall, a slightly smaller but no less baffling structure stretching 1.4 billion light-years. Like its Hercules counterpart, it flirts with the so-called end of greatness hypothesis, the idea that beyond a certain scale, the universe should become smooth and featureless. Yet these walls loom like mountain ranges in a landscape that was supposed to flatten into a prairie. Their existence suggests there's no end to greatness at all, just deeper layers of complexity waiting to be uncovered. But here's where the plot thickens. Both walls aren't just random clumps of galaxies. They're intricately linked to the voids around them, as if the emptiness actively shaped their growth. Simulations show that voids exert a kind of cosmic pressure, shepherding matter into filaments and sheets. It's like watching water drain around a bathtub's edges, swirling into patterns dictated by the empty space at its center. This dance between the densely packed walls and the voids they border raises a haunting question. Are we seeing the aftermath of some ancient cosmic battle where gravity and dark energy carved these structures into existence? The irony is delicious. These walls, meant to mark the limits of structure in the universe, instead reveal how little we grasp about its true architecture. They're not just curiosities, they're challenges written in starlight, daring us to rethink the rules we thought were set in stone. And with every new observation, the cosmos whispers back, the greatest walls aren't just barriers. They're gateways to the unknown. Galaxies should drift like leaves on a river, random, uncoordinated, each following the local ebb and flow of gravity. But in 2008, astronomers studying hundreds of galaxy clusters made a spine-tingling discovery. These clusters weren't just moving, they were being pulled. Across billions of light years, thousands of galaxies seemed to stream toward a single patch of sky near the constellations Centaurus and Vela, as if some unseen force beyond the edge of the observable universe was tugging them like a cosmic magnet. Researchers called it the dark flow, and if real, it threatens to upend one of cosmology's most fundamental assumptions, that the universe on the largest scales is isotropic, meaning it should look and behave the same in every direction. The evidence came from the cosmic microwave background, that ancient afterglow of the Big Bang. By measuring subtle distortions in the CMB caused by galaxy clusters moving through space, a phenomenon known as the kinematic Sunyaev-Zeldovich effect, scientists detected a peculiar pattern. Cluster after cluster showed motion aligned toward what's been nicknamed the dark hemisphere, a region of space with no obvious concentration of mass to explain the pull. It's as if an entire parade of galaxies is marching toward something we can't see, something outside our cosmic horizon. The implications are staggering. Could this be gravity leaking from another universe, or a superstructure so colossal it lies beyond the reach of our telescopes? Of course, extraordinary claims demand extraordinary evidence, and the dark flow has faced fierce skepticism. Critics argue it might be an artifact of incomplete data or calibration errors in the instruments. One study suggested that the observed motion could stem from our own Milky Way's movement, contaminating the measurements, like trying to spot a gentle breeze while riding a speeding train. Others point out that statistical noise, random fluctuations masquerading as a signal, might be to blame. After all, the universe is vast, and even rare coincidences can look intentional when you're sifting through petabytes of data. Yet the mystery hasn't faded. Subsequent analyses, including data from the Planck satellite, have both challenged and tentatively supported aspects of the dark flow. Some researchers now propose a middle ground, that the flow exists but it's localized, perhaps driven by immense superclusters we've yet to map fully. Imagine a mountain range hidden just beyond the fog. Its gravity could tug on nearby valleys without revealing itself. But if the dark flow is real, if galaxies are truly being drawn towards something beyond our view, then cosmology faces a watershed moment. It could mean our universe isn't the only one. It might hint at a multiverse where the gravity of neighboring cosmic bubbles ripples into our own. Or perhaps it's evidence of exotic physics, a flaw in Einstein's theory of gravity that only reveals itself on scales we've barely begun to probe. For now, the dark flow remains a tantalizing enigma, a shadow in the data that refuses to vanish, and that's what makes it so thrilling. In science, the most unsettling anomalies are often the ones that point to the next revolution. Quasars should be cosmic pinwheels spinning chaotically in all directions, their axes scattered randomly like stars in a wind-blown dandelion. But in 2014, astronomers peering into the void noticed something that sent a chill down the spine of cosmology. Hundreds of quasars, separated by billions of light years, were spinning in eerie alignment, their rotational axes pointing in the same direction like compass needles, all drawn to an invisible north. This discovery, dubbed the alignment of quasar polarizations, isn't just unexpected, it's impossible under our current understanding of the universe's structure. If the cosmos is truly random on large scales, as the cosmological principle insists, then finding such coordination across vast distances is like flipping a coin 1,000 times and getting heads every single time. At the heart of the mystery lies the sheer scale of the alignment. The quasars studied stretch across regions up to 4 billion light-years apart, a distance so vast it would take light twice the age of Earth to traverse it. Yet their black hole engines, the hyperactive cores powering these luminous beacons, appear locked in some silent cosmic choreography. One leading theory points to cosmic strings, hypothetical defects in space-time left over from the universe's birth. These ultra-thin, unimaginably dense filaments could have stretched across the early cosmos like cracks in freezing ice, imprinting directionality on matter as the universe expanded. If they exist, their gravitational influence might still linger, tugging quasars into alignment like puppets on unseen strings. Then there's the magnetic field hypothesis. Imagine a primordial field so vast it threads through the entire observable universe, its lines of force weaving through galaxies and voids alike. Such a field, generated in the universe's first moments, could have guided the rotation of nascent black holes, leaving them spinning in unison like iron filings aligned by a magnet. The problem: magnetic fields on this scale should have decayed long ago unless some exotic physics, perhaps linked to dark matter or dark energy, is keeping them alive. But not everyone's convinced. Skeptics argue the alignment could be an illusion, a trick of perspective where quasars appear coordinated due to our limited vantage point. Others suggest it might reflect a deeper bias in how we detect these objects, like hearing only the loudest voices in a crowd and mistaking them for a chorus. Yet each time researchers reanalyze the data, the signal persists, whispering of a universe far more interconnected or far more designed than we ever imagined. What if the alignment is a clue to something even grander? Some theorists speculate it could hint at a pre-Big Bang structure, a fingerprint of whatever existed before our universe began. Others wonder if we're seeing the shadow of a higher dimensional geometry, where our three-dimensional reality is just a slice of something much larger. Whatever the truth, the aligned quasars stand as a silent rebuke to our assumptions, proving once again that the cosmos reserves its strangest secrets for the voids between the stars. We know the universe is built on ordinary matter: protons, neutrons, electrons, the stuff that makes up stars, planets, and us. Scientists call these building blocks baryons, and according to our best calculations, they should account for about 5% of the cosmos' total mass-energy budget. But here's the problem: when astronomers tally up all the visible baryon stars, galaxies, gas, they come up short. Nearly half are missing. And nowhere is this mystery more glaring than in the cosmic voids, those sprawling deserts of emptiness where the rules of matter seem to have been rewritten. So where did all the baryons go? One leading suspect is the warm-hot intergalactic medium, or WIM, a ghostly web of superheated gas threaded between galaxies. Picture steam so thin it's nearly invisible, yet so vast it could cloak entire galactic superclusters. Theory suggests this gas, heated to temperatures between 100,000 and 10 million degrees, might harbor the missing baryons, its faint glow drowned out by the brighter lights of stars and galaxies. Detecting it is like trying to spot a candle behind a floodlight, but X-ray telescopes have begun picking up hints, faint absorption lines in the spectra of distant quasars, as if the WIM is casting shadowy fingerprints on the light passing through it. Yet even the WIM might not solve the full puzzle. Some voids are so empty, so devoid of any signal, that even this diffuse gas seems to vanish. That's led to wilder theories, like the idea that baryons could be hiding in ultra-cold molecular clouds, so frigid they emit almost no radiation. Or perhaps they've collapsed into exotic, dark matter-bound structures, invisible to our telescopes. There's even the radical notion that voids might act like cosmic sponges, soaking up ordinary matter and ejecting it beyond the observable universe through some unknown mechanism. The implications are profound. If baryons are truly missing from voids, it could mean our models of cosmic structure formation are fundamentally flawed. Simulations predict that voids should still contain trace amounts of matter, filaments of gas stretched thin but never fully broken. Yet when we look, we often find nothing, or at least nothing we can detect. It's like walking into a forest and finding the trees, the underbrush, even the insects, but realizing the air itself has inexplicably vanished. This isn't just about accounting for lost matter. The missing baryons could be a clue to something deeper, an overlooked force, a flaw in our understanding of gravity, or even evidence of matter decaying into unknown particles over cosmic time. Every time we refine our instruments, the hunt intensifies, but the voids keep their secrets close. They remind us that the universe's inventory is far from complete, and what we can't see might be just as important as what we can. The cosmic voids might seem like empty wastelands, but hidden within their vast expanses are peculiar residents that defy explanation: tiny, ghostly galaxies drifting in isolation and enigmatic blue stars burning violently with no neighborhood to call home. Among them, the void dwarf galaxies stand out as cosmic misfits. These faint, wispy collections of stars shouldn't exist according to our standard models of galaxy formation. Most galaxies, even small ones, are thought to be anchored by massive halos of dark matter, the invisible scaffolding that helps them hold their shape and survive collisions. But void dwarfs appear almost naked, lacking the dark matter they should have. It's like finding a house standing without a foundation, defying every law of physics we know. Take the galaxy NGC 1052 DF2, a ghostly smudge of stars floating in the void. Observations show its stars move so slowly that the galaxy should have torn itself apart long ago unless dark matter were holding it together. Yet when astronomers measured its mass, they found almost none. The implications are staggering. Could these dwarfs be remnants of ancient galaxies stripped bare by the void's emptiness? Or do they point to an alternative form of dark matter, one that behaves in ways we haven't yet imagined? Some theorists even suggest these galaxies might be failed fragments, cosmic orphans ejected during violent collisions billions of years ago, left to wander the voids alone. Then there are the isolated blue variables, massive, luminous stars burning fiercely in the middle of nowhere. These stars are so hot and bright they stand out like flares in the darkness, yet they're nowhere near the dense gas clouds where such stars typically form. One of the most famous, VFTS 682, is a monstrous blue giant with no business existing in its desolate patch of space. Normally, stars this massive form in bustling stellar nurseries, surrounded by the gas and dust of their birthplaces. But these loners appear to have materialized out of nothing, as if the void itself conspired to ignite them. How did they get there? One possibility is that they're runaway stars, flung from their home galaxies by gravitational slingshots during close encounters with black holes or other massive objects. Picture a cosmic game of pinball where stars are ejected at incredible speeds, destined to drift alone through the void. Another, more radical idea is that these stars formed in situ from rogue gas clouds, collapsing under conditions so rare we've yet to understand them. Or perhaps they're the last survivors of vanished dwarf galaxies, their siblings long since faded into the darkness. What makes both these phenomena so fascinating is their defiance of expectation. Void dwarfs challenge our understanding of dark matter's role in galaxy formation, while the blue variables force us to reconsider how and where stars can be born. Together, they paint a picture of voids not as true emptiness, but as cosmic laboratories where the universe experiments with its own rules. Every discovery here feels like finding a puzzle piece from the wrong box. It doesn't fit, and yet it might be the key to seeing the bigger picture. Gamma-ray bursts are the universe's most violent explosions, cosmic detonations so powerful they outshine entire galaxies for a few fleeting seconds. We've long assumed these cataclysms are born in the chaotic hearts of star-forming regions, where massive stars live fast, die young, and collapse into black holes or neutron stars. But nature loves a curveball, and the voids have delivered a stunner. GRBs flaring to life in the emptiest corners of space, far from the stellar nurseries that should have birthed them. These orphan bursts don't just defy expectations, they force us to rewrite the playbook on how GRBs form. Take GRB 150424A, a burst detected in 2015. When astronomers traced its origin, they found it nestled in a void so desolate that neighboring galaxies were almost non-existent. According to standard models, this shouldn't be possible. Long-duration GRBs, those lasting more than 2 seconds, are thought to arise from the collapse of massive, short-lived stars. But without dense star-forming gas clouds, how could such a star even exist? One radical explanation points to primordial black holes, hypothetical relics from the universe's first moments. These ancient, invisible objects might lurk in voids, occasionally devouring stray matter and unleashing bursts of gamma rays as their last supper. It's a fringe idea, but the voids have a way of making fringe ideas seem plausible. Then there's the neutron-star merger theory. When two neutron stars spiral together, their collision can produce a short-duration GRB. Normally, these mergers happen in galaxy clusters where neutron stars are plentiful. But if a binary pair got ejected into a void billions of years ago, their slow-motion death spiral could finally culminate in isolation. The problem: void GRBs often show characteristics of long-duration bursts which don't fit the neutron-star merger profile, unless, of course, our classification system is missing something. Perhaps the most unsettling possibility is that void GRBs are signs of something entirely new, a previously unknown astrophysical process lurking in the cosmic emptiness. Some theorists speculate about dark stars, exotic objects fueled by dark matter annihilation rather than nuclear fusion. Others wonder if voids amplify certain types of explosions by suppressing competing energy sources, like a silent room making a whisper sound like a shout. What makes these bursts so crucial isn't just their mystery, it's what they reveal about the universe's flexibility. If GRBs can ignite in voids, then our understanding of stellar life cycles, black hole formation, and even the distribution of matter might be incomplete. Every void burst we discover is a flare in the dark, illuminating just how much we still have left to learn, and in the grand emptiness, that might be the most thrilling discovery of all. Deep in the cosmic voids, where galaxies are scarce and darkness reigns, astronomers have stumbled upon something that shouldn't be there: beacons of intense radiation screaming across the emptiness. These are void megamasers, cosmic lasers on steroids, amplifying microwave light into blinding signals that defy logic. Normally, megamasers are born in the chaotic hearts of galaxies, where supermassive black holes churn vast disks of gas and dust, creating the perfect conditions for this rare phenomenon. But the void megamasers, they're orphans. No galaxy in sight, no obvious source of fuel, just a supermassive black hole lurking alone in the abyss, firing off beams of energy like a lighthouse in a deserted ocean. Take HO043 plus 046, one of the most baffling void megamasers ever detected. Floating in a region where the nearest galaxy is millions of light years away, this black hole weighing in at tens of millions of solar masses should have nothing to feast on. Yet it's not just active, it's thriving, powering a maser so bright it outshines anything else in its void. It's like finding a roaring bonfire in the middle of a desert with no wood for miles. How did this black hole get here? The leading theory suggests it might be the corpse of a failed galaxy, a structure that started forming billions of years ago but was ripped apart by the void's expansion before it could mature. Imagine a seedling trying to grow in salted soil, stunted, starving, yet somehow clinging to life. But that's not the only puzzle. Void megamasas often emit at frequencies that don't quite match their known galactic cousins, hinting at an environment far stranger than we've seen elsewhere. Some researchers speculate these black holes might be feeding on an exotic diet, perhaps streams of dark matter or primordial gas clouds left over from the universe's infancy. Others wonder if they're the remnants of ancient quasars, their host galaxies long since evaporated into the void, leaving behind their engines still running on fumes. Then there's the timing problem. Supermassive black holes take billions of years to grow to such colossal sizes, yet voids are supposed to be too empty to sustain their growth. Did these black holes form differently, perhaps in some violent collapse of early universe conditions we don't yet understand? Or could they have been flung into the void during galactic collisions, ejected with such force that they left their homes behind entirely? Every void megamesa we find is a challenge to our cosmic storytelling, proof that black holes don't always play by the rules. They force us to ask not just how they exist, but why. Are they accidents of cosmic evolution or signs of a deeper, hidden order in the voids? One thing's certain. In the great silence of the cosmic deserts, these screaming beacons refuse to let us ignore their mystery. At first glance, the odd radio circles or orc appear as faint, ghostly rings etched into the void's darkness, like ripples from a stone thrown into a cosmic pond. But these aren't just any radio emissions. Spanning hundreds of thousands of light years, these enigmatic structures glow in radio wavelengths while remaining utterly invisible to optical telescopes. Discovered in 2020, they've since become one of the most perplexing mysteries in modern astronomy, not just because of their strangeness, but because many of them seem to prefer the voids, those vast, empty regions where nothing else dares to linger. One of the most tantalizing ORCs, named ORC-1, sits in a void so sparse that its nearest neighboring galaxy is over 150 million light-years away. At that distance, any conventional explanation like the aftermath of a galactic collision or the shock waves of a supernova falls apart. There's simply not enough matter nearby to produce such a colossal, energy-hungry structure. It's as if the void itself decided to carve a perfect circle into the fabric of space, leaving astronomers scrambling for answers. Some theories suggest these rings could be the remnants of a titanic eruption from a supermassive black hole, a belch of energy so ancient its source galaxy has long since vanished. Others propose they're reverse shocks from dark matter annihilations, a process so exotic it sounds like science fiction. Then there's the wildcard hypothesis, one that's equal parts thrilling and unnerving. Could ORCs be the echoes of long-dead civilizations? The idea, while speculative, isn't entirely far-fetched. If an advanced species harnessed the energy of their entire galaxy in a final, desperate act, perhaps to escape a dying universe or send a message across time, the resulting shockwave might resemble what we're seeing. The rings would then be cosmic gravestones, markers of a civilization's last stand. It's a haunting thought, though skeptics rightly point out that natural explanations are far more likely. What makes ORCs even stranger is their uniformity. Unlike supernova remnants or radio galaxies, which come in chaotic shapes, these circles are almost perfectly symmetrical, as if molded by some unseen force. One leading theory suggests they're the result of a stacked explosion, multiple supernova detonating in rapid succession within a galaxy we can't see, their combined shock waves sculpting the radio rings like a chisel on stone. The problem: no known stellar population could produce such coordinated blasts without leaving behind other detectable traces. Another clue lies in polarization, the way the radio waves are oriented. ORC-1's emissions are highly polarized, a signature often linked to intense magnetic fields. This has led some researchers to propose that voids might amplify magnetic phenomena in ways we don't yet understand. Imagine a cosmic magnifying glass, bending and twisting magnetic fields until they snap into these bizarre, looped structures. Every new observation deepens the mystery. Recent studies have found ORCs overlapping with faint X-ray glows, hinting at incredibly hot gas, yet there's no visible source heating it. It's as if the voids are hiding entire chapters of astrophysics we've yet to read. Whether they're relics of lost civilizations, fingerprints of dark matter, or something entirely new, one thing's clear: the universe is still writing its rulebook, and the voids are holding the pen. Hidden in the vast nothingness of cosmic voids, silent giants drift clouds of hydrogen so diffuse they're practically invisible, yet vast enough to dwarf entire galaxies. These aren't just pockets of gas, they're cosmic phantoms, remnants of a time when the universe was still assembling itself, and their existence rewrites what we thought we knew about how galaxies form. Detected through their faint radio whispers emissions from neutral hydrogen atoms, known as HI, surveys these void clouds shouldn't exist in such isolation. According to our models, gas this sparse should have collapsed into stars billions of years ago or been torn apart by the void's expansion. Yet here they are, lingering like echoes of a forgotten era. Take the famous Levy cloud, a hydrogen structure so massive it spans over 2 million light-years, floating in a void with no galaxies nearby to anchor it. Without the gravitational pull of dark matter or the turbulence of neighboring stars, this cloud should have dissipated eons ago. Instead, it clings together, defying the odds. Some astronomers speculate these clouds are the skeletons of failed galaxies, regions where dark matter never clumped densely enough to trigger star formation, leaving behind only the ghostly imprint of their gas. Others propose something even stranger, that voids might harbor unique magnetic fields or exotic physics, somehow preserving these hydrogen relics in a state of suspended animation. Then there are the dark galaxies, another enigma lurking in the shadows. These are structures rich in hydrogen and presumably brimming with the raw materials for stars, yet almost completely devoid of starlight. They're like cosmic warehouses packed with fuel but never lit. One of the most puzzling examples is HI 448, a dark galaxy detected in the void between Leo and Coma Berenices. It contains enough gas to birth billions of stars, yet scans reveal only a handful, if any at all. It's as if the galaxy got stuck in first gear, its star-making machinery frozen mid-process. What's stopping these dark galaxies from igniting? One theory points to the voids themselves. In these desolate regions, gas may be too spread out and too calm to collapse under its own gravity, like a cloud too thin to rain. Another idea suggests that without the gravitational nudges from nearby galaxies' collisions and mergers that typically jumpstart star formation, these dark galaxies remain eternally dormant. But the most tantalizing possibility is that they're not dormant at all. Could dark galaxies be home to stars so dim, so unlike anything we've seen that our telescopes simply can't detect them? Imagine a stellar population born in the void's extreme isolation, stars built from different ratios of elements, burning colder and darker than the sun, invisible against the cosmic background. The implications ripple far beyond these lonely clouds and shadowy galaxies. If voids can preserve primordial hydrogen or halt star formation entirely, they might be the universe's best time capsules, holding clues to the conditions of the early cosmos. Even more provocatively, they could hint at unseen forces, perhaps a previously unknown interaction between dark matter and gas, or a subtle tweak to the laws of gravity under extreme low-density conditions. Every hydrogen cloud we find, every dark galaxy that flickers into view, is a piece of a puzzle we're only beginning to assemble, and in the hushed emptiness of the voids, these silent giants whisper a single, unsettling truth: the universe is far stranger than we ever dreamed. Cosmic rays are usually the universe's way of throwing high-speed particles at us, protons and atomic nuclei, accelerated to nearly the speed of light by supernova explosions, black holes, or other extreme cosmic engines. But in the voids, something peculiar happens. Occasionally, detectors on Earth record ultra-high-energy cosmic rays particles packing so much punch they shouldn't exist, and when astronomers trace their paths backward, they lead not to a bustling galaxy or a violent quasar, but to nothing. Empty space. These void cosmic rays are like bullets fired from a gun that isn't there, and their existence forces us to rethink where cosmic rays come from and what might be lurking in the voids to create them. The most famous of these mystery particles was dubbed the "Oh my God" particle, detected in 1991. With an energy 50 million times greater than the protons smashed in the Large Hadron Collider, it remains the most powerful cosmic ray ever recorded. When researchers followed its trajectory, they found no obvious source, no active galaxy, no gamma-ray burst, just the yawning emptiness of a cosmic void. It wasn't alone. Other ultra-high-energy particles have since been linked to voids, each one a cosmic paradox. How can nothing produce so much? One explanation points to top-down models, where these particles aren't accelerated by astrophysical sources, but are instead the decay products of something far more exotic. Picture a heavyweight champion disintegrating into a flurry of punches. The particles we detect might be the debris of primordial monstrosities like cosmic strings, magnetic monopoles, or even dark matter particles annihilating one another in the void's depths. These theoretical relics, left over from the universe's birth, could be decaying or colliding in the voids, unleashing showers of ultra-high-energy particles without any visible fireworks. Then there's the eerie possibility that voids aren't as empty as they seem. What if they're threaded with hidden networks of magnetic fields, invisible to our telescopes but strong enough to act as particle accelerators on a cosmic scale? In this scenario, even the sparse matter floating in voids could be whipped up to unimaginable speeds over billions of years, like leaves caught in a ghostly, galaxy-sized wind tunnel. The problem: magnetic fields this powerful should leave other traces, distortions in the cosmic microwave background perhaps, yet we've found nothing definitive. The most unsettling idea of all is that void cosmic rays might be messengers from beyond our universe. If extra dimensions or parallel universes exist, their physics could occasionally leak into ours, manifesting as particles with impossible energy. It's a long shot, but when the alternative is accepting that voids, the most barren places we know, are somehow generating the universe's most energetic particles, even wild theories start sounding plausible. Every time one of these void-born cosmic rays streaks through our detectors, it's a reminder that the emptiest places might hold the keys to the universe's most violent secrets. Whether they're the fallout of dark matter, the echoes of hidden magnetic storms, or something even stranger, these particles refuse to let us dismiss the voids as mere nothingness. After all, in the grand tapestry of the cosmos, sometimes the loudest screams come from the quietest places. Time dilation is supposed to be one of Einstein's most reliable predictions, the idea that gravity slows time itself, making clocks tick slower near massive objects like stars or black holes. Astronomers use this effect to measure cosmic distances, assuming the universe plays by consistent rules. But in the voids, something's off. Supernova, those brilliant stellar explosions used as cosmic mile markers, are flashing a warning sign. Their light, stretched by the expansion of space in a phenomenon called redshift, doesn't always match the time dilation we expect. Some appear to burn too fast or too slow, as if time itself stutters in the emptiness between galaxies. Take supernova 2003 FG, for example. Located in the heart of a sprawling void, its light curve, the way it brightens and fades, deviated sharply from models. Based on its redshift, the explosion should have unfolded at a predictable, stretched-out pace, its light diluted by cosmic expansion. Instead, it flashed like a camera bulb, its timeline compressed in ways that defy explanation. At first, astronomers dismissed it as a fluke, but then came supernova 2006 SR, then 2011 BY, each one a silent rebellion against the clockwork precision we thought governed the cosmos. The implications ripple far beyond a few misfit supernovae. If time dilation isn't behaving uniformly in voids, it could mean one of two terrifying possibilities. Either the fundamental constants of physics, the very rules of reality aren't as constant as we thought, or our interpretation of redshift, the cornerstone of modern cosmology, is fundamentally flawed. The first scenario would upend centuries of science. Imagine gravity weakening in voids, or the speed of light subtly shifting across cosmic deserts. It's like discovering the laws of chess change depending on which square you're playing on. The second possibility is no less unsettling. Redshift is how we measure the universe's expansion, and if we're misreading it, our entire cosmic timeline, the age of the universe, the nature of dark energy, even the fate of everything, might need recalibration. Some theorists suggest voids could distort light in unexpected ways, perhaps through interactions with undiscovered particles or warped spacetime geometries. Others wonder if the emptiness itself amplifies redshift, tricking us into thinking space is stretching faster than it truly is. Then there's the wild card. What if these anomalies aren't errors at all but clues? Princeton physicist Paul Steinhardt once proposed that varying constants could signal a collision with another universe, a bruise left on our physics. It's a fringe idea, but voids, with their eerie quiet and borderline impossible structures, have a way of making the fringe feel plausible. Every anomalous supernova in the voids is a ticking time bomb for cosmology. They force us to ask whether our cosmic map is drawn in vanishing ink, its landmarks shifting under our gaze, and in the silence of those empty spaces, time itself might be whispering secrets we're only beginning to hear. Gravity is supposed to bend light, that much we know. Massive objects like galaxies and black holes warp spacetime, creating cosmic magnifying glasses that distort the light of objects behind them. But when astronomers turned their telescopes toward the voids, they found something bizarre. Patches of nothingness bending light as if they were packed with invisible matter. These void gravitational lenses shouldn't exist. According to general relativity, empty space shouldn't have enough mass to twist light beams. Yet there they are, ghostly imprints on the sky, warping the light of distant galaxies in ways that defy every prediction. Take the case of a void near the constellation Aquarius. When researchers mapped the light from galaxies behind it, they found subtle distortions, tiny smears and stretches in the starlight that suggested something was bending spacetime. But when they tallied up the visible matter in the void, there was barely enough to account for even a fraction of the lensing effect. It's like looking at a funhouse mirror and realizing the glass is bending without anyone holding it. This anomaly has split cosmologists into two camps: those who believe the voids must be hiding unseen mass, and those ready to rewrite the laws of gravity itself. The first group points to dark matter as the culprit. If voids contain vast, diffuse halos of invisible particles, they could explain the lensing without contradicting Einstein. But there's a catch. Simulations show that dark matter should be less concentrated in voids, not more. It's the opposite of what we'd expect, like finding a dense fog in the middle of a desert. Some theorists suggest exotic dark matter flavors, particles that behave differently in low-density environments. Others propose that dark matter might clump in ways we haven't modeled, forming invisible tendrils threading through the void like spider silk. Then there's the rebel faction scientists who argue the lensing might be evidence that gravity itself works differently in voids. Modified Newtonian dynamics, or MUND, offers an alternative. This theory suggests that on cosmic scales, especially where gravity is weak, Newton's laws break down and a tweaked version of gravity takes over. In the near-nothingness of a void, where the gravitational pull is almost non-existent, MUND predicts subtle shifts in how light bends. It's a radical idea, but the void lensing data fits Mund predictions suspiciously well. Critics dismiss Mund as a band-aid, a fix that only works in specific cases without explaining the broader universe. Yet the voids keep whispering otherwise. Some of the most compelling evidence comes from redshift measurements. If dark matter were causing the lensing, we'd expect the effect to vary with distance in a predictable way. But in voids, the distortions don't always follow the script. A few studies have even found lensing in reverse, where light appears repelled rather than bent, something neither dark matter nor Mund easily explains. So where does that leave us? With a cosmic tug-of-war between two worldviews? One clings to dark matter, forcing it into increasingly convoluted shapes to fit the data. The other dares to question gravity itself, risking the foundations of modern physics. And in the middle, the voids loom, their empty hands twisting starlight into riddles we're only beginning to decode. One thing's certain: if the universe's emptiest places can bend light, then darkness might hold more power than we ever imagined. Quantum foam, the seething, frothy turbulence of spacetime at the tiniest scales, is one of the most elusive concepts in modern physics. Theorized to churn with virtual particles popping in and out of existence, it's a hallmark of quantum gravity, the missing link between Einstein's relativity and the quantum world. But detecting it has always seemed impossible. The energy required to probe such infinitesimal scales is far beyond our reach unless, of course, the universe handed us a natural amplifier. Enter the cosmic voids. These vast, near-empty regions might be the perfect laboratories to catch whispers of spacetime's granularity, where quantum foam could leave fingerprints on a scale we can finally observe. The idea hinges on emptiness itself. In the crowded cosmos, quantum fluctuations are drowned out by the noise of stars, galaxies, and radiation. But in the voids, where matter is sparse and gravity's grip is weakest, these tiny fluctuations might stretch and swell, magnified by the absence of competing forces. Picture ripples on a pond. Toss a pebble into a stormy ocean, and the waves vanish into the chaos. But drop that same pebble into a still, isolated pool, and the ripples spread clear and undisturbed. That's the promise of voids. Their stillness could let us see the subtle tremors of spacetime itself, fluctuations that would otherwise flicker unnoticed in the cosmic background. One tantalizing clue comes from loop quantum gravity, a theory suggesting spacetime isn't smooth but woven from tiny, discrete loops. If true, voids might reveal this granularity through anomalies in how light travels across their emptiness. Photons traversing a void could encounter microscopic bumps in spacetime, subtly altering their paths or energies in ways that defy classical physics. It's like rolling a marble across a table. On a perfectly smooth surface, it glides predictably. But if the table were invisibly textured, the marble might wobble or slow in ways that betray the hidden roughness. Already, astronomers have spotted bizarre energy shifts in void-crossing light that can't be explained by known physics. Could these be the first hints of quantum foam's texture? Then there's the dark energy connection. If quantum foam fluctuates wildly enough, some theories suggest it could mimic the repulsive force we attribute to dark energy, the very force accelerating the universe's expansion. In voids where dark energy dominates, these fluctuations might be amplified to observable levels. Imagine blowing up a balloon covered in microscopic cracks. As it inflates, the cracks stretch into visible seams. Similarly, as voids expand, their quantum imperfections might stretch into detectable signatures, offering a backdoor to test theories that were once purely mathematical. Critics argue the signals are too faint, the noise too great, but recent advances in quantum sensors and precision cosmology are turning the impossible into the plausible. Projects like the Square Kilometre Array, with its unparalleled sensitivity to subtle radio distortions, or next-gen cosmic microwave background experiments hunting for void-imprinted anomalies, could finally catch spacetime in the act of flickering. And if they do, the implications are staggering. Confirming quantum foam in voids wouldn't just validate loop quantum gravity. It could rewrite our understanding of reality's fabric, proving that even the emptiest corners of the cosmos are alive with the universe's tiniest tremors. What makes this search so thrilling isn't just the science, it's the irony. We've spent centuries studying the universe's brightest, noisiest objects to uncover its secrets. But the answers we crave might be hiding in the silence, waiting for us to learn how to listen. Neutrinos are the universe's most elusive particles, tiny, nearly massless ghosts that slip through planets like they're not even there. Trillions pass through your body every second, leaving no trace, but in the cosmic voids, something strange is happening. Detectors buried deep underground and beneath Antarctic ice have begun picking up an excess of neutrinos, far more than our models predict. And when astronomers trace their paths backward, they don't lead to supernova, black holes, or any known cosmic engine. They point to nothing, the vast, empty stretches of voids where neutrinos shouldn't be pouring forth in such numbers. This anomaly, dubbed the void neutrino excess, isn't just a statistical hiccup. It's a potential crack in the foundation of particle physics, hinting at forces or particles beyond anything we've ever seen. The first clues surfaced in data from IceCube, the neutrino observatory embedded in the South Pole's ice. While most neutrinos could be traced back to violent astrophysical sources, a stubborn fraction seemed to originate from voids, regions where even the thin soup of intergalactic gas is barely present. At first, researchers dismissed it as noise, but as more detectors came online, the signal grew louder. In the Boötes Void, the Lynx Supervoid, and others, neutrino counts spiked in ways that defied explanation. It's like walking into a desert and finding a geyser erupting from dry sand. So where are these rogue neutrinos coming from? One leading theory points to sterile neutrinos, hypothetical particles even more ghostly than their ordinary cousins. Unlike regular neutrinos, which interact via the weak nuclear force, sterile neutrinos would feel only gravity, making them nearly impossible to detect directly. But if they exist, they could decay into ordinary neutrinos, creating the excess we observe. Voids, with their extreme low-density environments, might be the perfect places for this decay to occur, free from the interference of other particles. It's a tantalizing idea because sterile neutrinos could also solve another cosmic mystery, dark matter. If they're heavy enough, they might make up the invisible scaffolding of the universe. But not everyone's convinced. Skeptics argue the excess could stem from misaligned cosmic rays or instrumental artifacts, like echoes in a cavern mistaken for voices. Others propose even wilder explanations. Could voids be harboring primordial black holes, so tiny and ancient they evaporate via Hawking radiation, spraying neutrinos as they fade? Or perhaps the neutrinos are evidence of pseudo-sterile particles, exotic variants that oscillate between normal and sterile states under conditions unique to voids. The most radical possibility, these neutrinos aren't from our universe at all. If parallel dimensions or brain-world cosmologies are real, voids might be the thinnest membranes separating us from them, places where particles from another reality occasionally leak through. It sounds like science fiction, but when the data refuses to fit the mold, even fringe ideas deserve a hearing. What makes the void neutrino excess so electrifying isn't just the mystery, it's the stakes. If sterile neutrinos are confirmed, they'd be the first major addition to the standard model of particle physics in decades, reshaping our understanding of the universe's most fundamental building blocks. And if the explanation lies even deeper, in hidden dimensions or new forces, we might be standing on the brink of a revolution as profound as quantum mechanics or relativity. For now, the voids keep sending their silent signals, each one a whisper from the dark, daring us to listen. The universe's emptiest places shouldn't have magnetic fields. After all, magnetism arises from moving electric charges, electrons zipping through wires, ions swirling in stellar plasma, the churn of galactic dynamos. But in the cosmic voids, where matter is nearly absent and galaxies are few and far between, astronomers have detected faint but undeniable magnetic signatures stretching across millions of light-years. These void magnetic fields are like whispers in a soundproof room. They shouldn't be there, yet they persist, threading through the darkness with no obvious source. Their existence forces us to confront a glaring gap in our understanding. How can magnetism survive, let alone thrive, in the most desolate reaches of space? One possibility is that these fields are primordial relics from the universe's fiery birth. In the first fraction of a second after the Big Bang, quantum fluctuations might have generated microscopic magnetic fields like sparks flickering in the cosmic dawn. As the universe expanded, these fields could have stretched to unimaginable scales, preserved in the voids like fossils in amber. It's a compelling idea, but there's a catch. Magnetic fields should decay over time unless they're actively reinforced by moving charges, and the voids offer almost no material to sustain them, unless, of course, something we can't see is at work. Some theorists speculate that dark matter, if it interacts weakly with electromagnetism, might play a role, its invisible currents stirring the fields like a ghostly hand. Then there's the galactic outflow theory. Even in voids, a few lonely galaxies cling to existence, and their supermassive black holes can belch jets of charged particles at near light speed. These outflows might inject magnetic energy into the void like ink spreading through water. Over billions of years, these tendrils could weave a diffuse web of magnetism, faint but vast. The problem: most void galaxies are too dim, too quiet to account for the fields we observe. Their outflows should fizzle long before reaching the scales we're detecting. Unless voids amplify these signals somehow, turning whispers into echoes, perhaps the most radical explanation is that void magnetic fields aren't primordial or galactic at all, but cosmic. Some models suggest that the large-scale structure of the universe itself, the filaments and voids, could generate magnetism through the motion of ionized gas sloshing across cosmic tides. Picture a river flowing through a canyon. Even if the water is sparse, its movement can carve channels over time. Similarly, the slow, collective motion of particles across voids might generate weak currents, sustaining magnetic fields against all odds. What makes these fields so fascinating isn't just their mystery, it's their potential as cosmic archaeology. If they're primordial, they could be a direct window into the universe's first moments, untouched by the chaos of stars and galaxies. If they're sustained by unknown physics, they might hint at exotic particles or hidden forces. And if they're proof of large-scale dynamos, they could redefine how we think about the cosmos structure. But the real surprise: these fields might not be mere curiosities. Some simulations suggest void magnetism could influence galaxy formation, guiding gas flows and star birth across millions of light years. They might even leave subtle imprints on the cosmic microwave background, the afterglow of the Big Bang. If so, the emptiest places in the universe could be quietly shaping its brightest. Every new detection deepens the puzzle. Recent observations from radio telescopes like LOFAR have mapped void fields with unprecedented precision, revealing structures so vast they defy simple explanation. Some regions show bizarre twists and kinks, as if the fields were tangled by some ancient turbulence. Others align in sweeping arcs like cosmic brushstrokes painted across the void. Whether they're fossils from creation, echoes of galactic winds, or something entirely unforeseen, one thing is clear: the voids aren't truly empty. Even in the deepest darkness, the universe hums with unseen forces, and magnetism might be its quietest, most persistent song. What if the cosmic voids aren't just empty spaces, but the most valuable real estate in the universe? The void life hypothesis dares to suggest that advanced civilizations, if they exist, might not cluster around stars like we do. Instead, they could thrive in the darkness, harnessing the void's near-perfect emptiness for reasons we're only beginning to grasp. It's a radical idea, but when you consider the advantages, the logic is chillingly compelling. First, there's energy. In a void far from the blinding light of stars, an advanced society could exploit the universe's coldest temperatures, at just a few degrees above absolute zero, to create ultra-efficient quantum computers or exotic matter states impossible to achieve elsewhere. The near absence of gravity from nearby galaxies would also make it easier to construct megastructures on scales we can barely imagine. Take Dyson Sphere's hypothetical energy harvesting shells built around stars. In a void, a civilization might not need stars at all. Instead, they could tap into the void's sparse hydrogen clouds or even dark matter itself, using technologies so advanced they border on magic. Then there's privacy. For a species wary of cosmic threats, hostile civilizations, gamma-ray bursts, or the heat death of the universe, a void offers the ultimate hideout. With no nearby galaxies to observe them, they could experiment, expand, or even evolve in total secrecy. Some astronomers have already spotted anomalous infrared sources in voids, objects glowing faintly with no visible stars to explain the heat. Could these be Dyson spheres built around black holes, their creators drawing energy from the void's nothingness itself? But the most tantalizing clue might be the void's unnatural uniformity. Some regions, like the KBC Void, are so vast and symmetrical they almost seem engineered, as if something or someone has been sculpting them over eons. If a civilization reached level 3 on the Kardashev scale, able to manipulate energy on galactic scales, reshaping voids would be trivial. They might even use them as cosmic batteries, siphoning dark energy or redirecting spacetime itself. Of course, skeptics argue that voids are too resource-poor to sustain life. Yet nature thrives in Earth's most extreme environments, from deep-sea vents to Antarctic ice. Why wouldn't intelligence adapt to the void's unique conditions? Maybe we're looking for life in all the wrong places, scanning star systems when the real action is happening in the dark. The void life hypothesis forces us to rethink not just where life could exist, but what it might become. If civilizations eventually outgrow their stars, the voids could be the next frontier, silent, infinite, and waiting. And if we ever detect a signal from the emptiness, it might not be a distress call. It could be a message from the future. The cosmic microwave background, the faint glow of the Big Bang's aftermath, should be a smooth tapestry, its slight temperature variations tracing the seeds of all future galaxies and voids. But when astronomers focus on the voids, they find something unsettling. Embedded in these empty regions are peculiar ripples in the CMB, subtle distortions that don't match the patterns seen elsewhere. These anomalies, often dismissed as noise in earlier studies, are now impossible to ignore. Some researchers propose they're echoes of a time before the Big Bang, ghostly imprints of a previous cosmic cycle, or evidence of a collision with another universe. Take the so-called void polarization anomalies, first spotted in data from the Planck satellite. In certain voids, the CMB's light shows unexpected twists in its polarization, the orientation of its electromagnetic waves. These twists align in ways that defy standard inflationary models, as if space itself remembers a pre-Big Bang structure. One theory suggests these patterns could be scars from a bounce, a moment when a prior universe collapsed and rebounded into our own. Imagine a sheet of paper crumpled and smoothed. The creases might fade, but under the right light, their shadows remain. Then there's the cold spot connection. Some voids correlate with unusually cold patches in the CMB, regions where the temperature dips more than our models can explain. While we've touched on this earlier, the implications run deeper. If these cold spots aren't just random fluctuations but instead bear signatures of pre-Big Bang physics, they could hint at a cyclic cosmology, a universe that expands, contracts, and rebirths in an endless loop. The voids in this scenario might be the universe's way of preserving fragments of its past, like an author scribbling marginal notes between drafts of a story. Skeptics argue these anomalies could stem from foreground interference or instrumental quirks, but the more we refine our observations, the stranger the data becomes. Recent studies using machine learning to filter out noise have isolated patterns in void CMB data that resemble concentric rings, features some theorists liken to Hawking points, hypothetical remnants of black holes from a prior universe. If true, these rings would be cosmic bullet holes, evidence of a violent, cyclical history written in the void's emptiness, the most radical interpretation. Voids aren't just empty space, they're windows. In string theory, higher dimensional brains could collide, birthing universes like ours. The voids might be thin spots in our brain's fabric, where echoes of other realities leak through. It's a wild idea, but when the data refuses to fit the mold, even wild ideas deserve a seat at the table. What makes these echoes so electrifying isn't just their potential to rewrite cosmology, it's the irony. The universe's quietest places might be its most talkative, whispering secrets from a time before time. And if we learn to listen, the voids could tell us stories we've never dared to imagine. The Fermi paradox has haunted astronomers for decades. If the universe is teeming with potential for life, where is everyone? The eerie silence might have an unexpected answer: the cosmic voids. These vast, empty regions could be more than just barren stretches of space. They might be the universe's ultimate sanctuaries, deliberately preserved by advanced civilizations as cosmic nature reserves. Think of it like a galactic Yellowstone, a place where intelligence thrives in deliberate isolation, shielded from the chaos of crowded star systems. Consider the logic. A civilization advanced enough to harness the energy of stars or black holes would eventually face existential threats, wars over resources, gamma-ray bursts sterilizing entire regions, or the slow heat death of the universe itself. The solution: relocate to the voids. Here, far from the gravitational tug-of-war of galaxy clusters, a species could engineer self-sustaining habitats on scales we can barely fathom. Imagine Dyson swarms, vast constellations of energy-collecting satellites built not around stars but suspended in the void, drawing power from the sparse hydrogen clouds or even the quantum fluctuations of spacetime itself. The void's near-perfect vacuum would also allow for unimaginably efficient computation, with quantum machines running at temperatures close to absolute zero, free from the interference of cosmic radiation. There's precedent for this in nature. On Earth, some of the most resilient ecosystems thrive in the most extreme environments: deep-sea vents, acidic hot springs, frozen tundras. If life can adapt to those conditions, why wouldn't intelligence seek out the void's unique advantages? The absence of competing civilizations, the near-zero risk of cosmic collisions, the limitless space for expansion. It's the ultimate real estate for a species thinking in billion-year timescales. Even our own detection methods might explain why we haven't found void dwellers. Our search for extraterrestrial intelligence has always focused on star systems, scanning for radio signals or technosignatures like megastructures. But a void-based civilization wouldn't need to broadcast its presence. With no nearby stars to obscure their activities, they could operate in perfect stealth, their energy signatures diluted across light years of emptiness. The most tantalizing clue might lie in the void's unnatural features. Take the KBC Void where we reside, a region 7 times larger than average, suspiciously sparse in galaxies. Could this be more than coincidence? Some theorists suggest it's evidence of a cosmic zoning law, a deliberate clearing of space by a civilization that values isolation. Others point to the void's near-perfect spherical shape, a geometry rarely seen in nature but easily engineered by intelligence. Of course, skeptics argue that voids are too resource-poor to sustain advanced life. But that assumes life as we know it. A post-biological civilization might transcend the need for planets or stars, existing as pure information in the void's cold expanse. Their cities could be networks of quantum-entangled nodes, their bodies clouds of nanomachines riding magnetic fields. To them, the voids wouldn't be empty, they'd be paradise. The implications are staggering. If the Fermi paradox's solution lies in the voids, then our search for extraterrestrials has been looking in all the wrong places. Instead of scanning star clusters, we might need to listen to the silence itself, tuning our instruments to the faint hum of a universe where intelligence isn't just out there, it's hiding in plain sight, in the last places we'd ever think to look. The cosmic voids have teased us with their mysteries for centuries, but the era of answers is finally within reach. A new generation of telescopes and missions, armed with unprecedented sensitivity, is turning its gaze toward these empty expanses, ready to peel back the layers of nothingness to reveal what truly lies beneath. Leading the charge is the James Webb Space Telescope, humanity's most powerful eye on the infrared universe. While JWST has already dazzled us with images of distant galaxies and newborn stars, its most revolutionary work might yet come from the void. Imagine probing the faint, redshifted light of galaxies skirting the edges of the Boötes Void, hunting for distortions that betray hidden matter or exotic physics. Or dissecting the spectral fingerprints of lone stars drifting in the emptiness, their chemical makeup preserving clues to the void's primordial origins. Webb's ability to see through cosmic dust and peer deeper into the infrared where the universe's oldest light lingers could finally settle debates about void formation, dark energy's role, and even those tantalizing hints of pre-Big Bang echoes. But the revolution doesn't stop there. On the horizon looms the Square Kilometre Array, a radio telescope so vast it will span continents, its thousands of antennas tuned to the faintest whispers of the cosmos. The SKA's true power lies in its ability to map the universe's large-scale structure in exquisite detail, tracing the distribution of hydrogen gas across billions of light years. In voids where this gas is sparse but potentially laced with secrets, the SKA could detect subtle ripples in space-time or magnetic fields woven through the emptiness like invisible threads. It might even spot the elusive warm-hot intergalactic medium, the WIM, finally accounting for the missing baryons that have haunted cosmology for decades. And if void megamasers or odd radio circles emit their faint signals, the SKA won't just hear them. It will decode their origins with precision never before possible. These missions are just the beginning. The upcoming Nancy Grace Roman Space Telescope, with its wide-field surveys, will hunt for supernova in voids, testing whether time dilation truly wavers in the cosmic deserts. Meanwhile, next-generation gravitational wave detectors like LISA could sense the ripples from black hole mergers in voids, probing whether their dynamics differ from those in denser regions. Even particle detectors like IceCube and future neutrino observatories are refining their aim, ready to pinpoint the sources of those enigmatic void-born neutrinos. Together, these instruments form a web of scrutiny, each thread tightening around the void's mysteries from a different angle. What makes this moment so electrifying isn't just the technology, it's the stakes. Voids are more than cosmic oddities, they're stress tests for our entire understanding of physics. If dark energy behaves differently in these empty regions, or if gravity weakens where matter is sparse, the implications would ripple through every textbook. The void's extreme environments act like cosmic particle colliders, stretching theories to their breaking points. And with each new observation, we're not just filling gaps in our maps, we're rewriting the rules of reality itself. The greatest irony, the universe's emptiest places might soon become its most revealing. As these missions unlock their secrets, the voids could transform from cosmic afterthoughts into the ultimate laboratories, proving once again that in the grand tapestry of the cosmos, darkness holds just as much wonder as light. From the eerie silence of the Boötes Void to the ghostly alignments of quasars spinning in unison, these 25 cosmic riddles aren't just curiosities, they're missing pieces in the grand puzzle of existence. Each void-born anomaly whispers the same unsettling question: What if the universe's emptiest places are hiding its most profound secrets? Whether it's dark energy warping time in supervoids, neutrinos streaming from nowhere, or light bending where nothing should exist, these phenomena force us to confront the limits of our understanding. Could voids be cracks in spacetime where multiverses leak through? Laboratories for exotic physics we've yet to imagine, or even the chosen refuge of civilizations too advanced for us to recognize? The beauty of these mysteries lies in their defiance. They refuse to fit neatly into textbooks or simulations, demanding we rethink everything from gravity to the nature of reality itself. Every time we point a telescope into the void, it sends back riddles wrapped in darkness, cold spots that shouldn't be there, galaxies without dark matter, magnetic fields with no source. It's as if the cosmos is teasing us, leaving breadcrumbs in the most unlikely places. So where do we go from here? The next decade of astronomy promises breakthroughs, with instruments like the SKA and Roman telescope poised to dissect these enigmas. But the real adventure lies in the questions we haven't even thought to ask yet. Maybe the voids aren't just empty space. They're the universe's way of keeping its deepest truths just out of reach, waiting for us to look closer. Now it's your turn. Which of these void phenomena keeps you up at night? Are you Team Multiverse, convinced cold spots are bruises from cosmic collisions? Or do you think dark energy's fingerprints are all over the KBC Void? Drop your wildest theories in the comments, because in the grand game of cosmic detective work, every perspective might just be the key to unlocking the next great discovery. And if you're hungry for more deep space mysteries, hit subscribe. The universe is stranger than fiction, and we're just getting started.